twist and turn it into doing something unexpected, and that is the end goal. So before we start twisting and turning, we need to understand what happens internally. So this is the function that you can call from user space, and everything else happens inside kernel. This is the boundary. Before this, it is in user space. Below this, it is in kernel. So inside this, kernel has this common handler. So whether you use execv or execv at, both land at the same function. Okay, and then it prepares some internal data structures which basically allows kernel to do rest of the stuff, and then basically this execution function is called, and then this particular function that is doing the execution, it does a lot of stuff. First part is obviously trying to figure out which type of file is this. Is it ELF? Is it statically linked, dynamically linked? If it is dynamically linked, is there any known interpreter for this? If it is a script, in that case, it will also do this part. Okay, that if this is a plain text file and there is first line starting with this one, so all that stuff will happen inside this one, and then obviously it will basically do the loading part for static binary. Internally, kernel knows how to load a file only for statically linked ELF. Everything else is piggybacked on that. For dynamically linked, there will be some sort of binary interpreter. For ELF, that will be RTLD, and then again that is statically linked. That kernel knows how to load, and then it will let that interpreter do all the necessary legwork to load a dynamically linked executable. Same goes for process for a script. It will find that interpreter, it will start, and then the same check happens again. If it is statically linked, it will load it directly. If it is dynamically linked, it will try to find its interpreter, which better be static, and once it is static, it will start that process, and then that process will do rest of the stuff to start next process, so on and so forth. So kernel knows only static ELF, and rest of the stuff is basically piggybacked on top of it. And then in load binary, there are a lot of function pointers that are configured at time of execution. So this part is something that okay. Now here there is one more interesting part, and there are structures like this which define how many formats kernel can handle. Okay, and that basically means that if somehow, how exactly we will pull it off, that is entirely different matter. But in theory, if somehow we can manipulate the chain of this structure, which tell kernel various types of binaries, whether it is static linked, dynamically linked, or a script file or whatever. If we can modify this chain, we can achieve two things. One, we can inject support for our own file format inside kernel. Okay, that means that on surface it will look like a PDF getting executed or a video file getting executed. Obviously, blue team people will not really be able to make sense of it, because executing a video doesn't really make any sense. But since we are manipulating the kernel directly, we can somehow make it make sense. That is one part. Second part is that if we are going to modify this thing, we can make it do something extra. Instead of giving it our own custom format to execute, we can hijack some handler for already known format, and we can probably try to make it do something extra. So for example, for statically linked ELF, there is this ELF binary function that is already defined in the kernel. Similarly, for a script, there is load a script function, and this is where that shebang is actually checked. So if you see the code here in the load script, this is again inside the kernel, we have this particular check. remaining lines are basically stripped off, and here you see that first character should be this and second one is this, and if it is not the case it will basically return some sort of error. Then in the chain we see this interesting entry and it says MISC format, and then there is nothing extra going on here. Problem is we already know ELF, we already know statically linked stuff, dynamically linked stuff, we already know the script part, but for some weird reason no one ever talks about this. You enroll in any course in Linux, whether it is basics, offside, advanced, intermediate, programming, red team, blue team, absolutely anything. A lot of courses will talk about rest of the formats, ELF, a script file, but no one is talking about this. Why?
Maybe it's hard to comprehend.
Nothing in life comes easy. It was not very easy for you to learn how to walk.
Yes.
Right? So by that logic, we should not learn how to walk, we should not learn how to drive, we should not learn how to ride a motorcycle, we should not learn computers. I mean, see that stupid keyboard, it has like more than 100 keys. How do you know when to press which particular key? It was hard. Yet you learned it. So why no one talks about this? Despite Linux being open source, why is this part basically hidden from OpenView? Is there something wrong with this? Because people are stupid. That is why they don't talk about it. Okay, now if we go inside the this system call, so eventually these function pointers will be called here and all that loading stuff will happen, and then here you see trying to figure out whether there is interpreter associated with that or not for dynamically linked one, and then if there is interpreter, what it will do, it will basically make that interpreter primary executable, and then the interpreter will do rest of the stuff. If it is statically linked, then basically it will start allocating memory, start setting permissions, and start mapping data from that ELF for execution. Then comes this RTLD part for dynamically linked, and as I said earlier, it is again statically linked because this is the only format that kernel knows how to load natively. Otherwise, we will basically end up in a never-ending loop, and this can be handled by kernel just fine. And whatever happens after this is done by this interpreter, which means that rest of the part is again inside user mode. We are outside kernel mode now. So what it will do, it will basically do some checks whether it is started as independent process or it is started by kernel, and then it will basically start going through some list whether there is some preload specified or not. So if you have ever used something like ld preload, ld.so.preload file or ld library path, all that stuff happens somewhere around these lines. And then if there is something specified in the preload, it will be loaded beforehand, so that your ld preload stuff that you are so familiar with, that is handled basically here, and this part is done by RTLD. Okay, which means that if I modify this thing, I can make it do something else here, and that also means that I can make it preload stuff without specifying ld preload. And blue team people love ld preload because it is very much visible like a sore thumb. They see that and they like Operation Smackdown. We identified a threat. and that is why we can do something like modifying this is open source. So we can basically tag extra entries in this preload list and let it do the preload without specifying LD preload or basically any of the LD variables. This particular file again, this is handled in the similar way. So it will read the entire file and then it will basically split it around semicolon and then it will basically load everything. And finally, this is our C runtime. There will be some relocation if it is required. It is not necessarily that it will get relocated. It will be relocated only when there is some sort of conflict, as in there is some overlap in the memory range where two shared objects are basically overlapping. So whichever comes later, it has to be relocated. And then there are other dependencies which will be loaded and relocated as required. And then there is some extra bookkeeping, accounting stuff, thread local storage in case it is multi-thread stuff. So all that stuff will happen. Then this libc is initialized. It will do its own initialization, and then the execution basically starts. So that is how process starts. And now we are back to that binfmt part which we discussed. Oh, किधर गया भाई? This one. So this one is called actually binfmt, and okay. So what it is, it basically is a feature from kernel which allows us to specify some sort of interpreter for pretty much any other file, which in turn allows us to define our own executable file formats. Okay, so script part is already done. So this is generally used by the various Java applications. They will associate their Java interpreter via this binfmt, and after that you don't have to even know that the path that you are trying to execute, it is not a standard ELF, it is a Java binary, but you just specify the path and rest of the stuff happens behind the curtains. So it is not something that is not used. It is routinely used by various packages written in Java, written in .NET, written some even written in Python, which come with their own Python interpreters. Then there are tools which allow you to execute Windows process on Linux. Those also use this thing. Yes.
Is it any different from SUID at least?
It is wildly different. For yes, for SUID, the file that you are setting SUID bit on, it already has to be executable in some particular way. If it is not executable, there is no point setting that SUID bit.
So
It allows you to make any file format executable. You want to execute a video, you want to specify that video file in execv, and you want it to open in some sort of video player, you can do that here.
but the kernel will disallow if we try to invoke it directly from the shell, right? Without
No,
executing
once you configure this, you can invoke it directly from the shell.
from the shell.
Yes.
So for the exe files, for example, if I put it in binfmt, so how would it be loaded on the memory? Because that exe will have
The kernel will load the interpreter will load your exe.
but the libraries will be different, right? Because for example, if I have a C program, it will just do libc.
The interpreter has to be Linux native,
Okay.
and rest of the headache is on interpreter's part, not kernel's part. So for binfmt, it is actually very easy. You need to first check if it is enabled. If not enabled, you can enable it, and then you have to write some string in this particular format. This is the name that you are going to give it to your mapping. This is to denote whether you want to identify the file type based on its extension or some sort of magic byte sequence. Then this is offset for magic byte. It is skipped for extensions, and then this is the magic byte itself that you want to check for. This is mask, again applicable only for magic bytes in case you want to basically ignore certain bits from the magic bits. Then this is absolute path for the interpreter that you want to get started as interpreter. Once someone tries to execute a file which is defined by this, and then there are some extra flags that you can set to indicate in which particular way you want to specify start this particular interpreter. And then you prepare this string, you write it at this magical location, and this thing is basically registered. Okay, that is all that you have to do. For RTLD part, that becomes more headache inducing. So this is runtime loader basically. On Linux this will be ld.so or something like this, and this is basically a dynamic linker which deals with loading the shared objects, symbol resolution, relocation, all these extra features like this. This is again something that blue team people really love a lot, because this allows them to see which process is loading which particular shared object and in which particular order, and it also allows them to allow or deny some shared object from getting loaded. But the catch is that this is again coming from here, and if we are going to modify this, we can disable that, or we can selectively disable that. Same goes for this one as well, this one as well, this one as well, this as well, and obviously this one. So all the goodies that we take for granted in Linux, whether it is for blue team or red team, a lot of those are coming from RTLD, which is running entirely in user space and is open source and is not really difficult to modify. So it is time to stop blindly trusting these, and now time to see what we can do with this binfmt and that RTLD part. So for binfmt, what we want to do, we want to execute a plain text file just for sake of example. And what we want to do, when we execute that plain text file, we want it to open inside this less utility. Okay, so for sake of ease, we say that the file should start with first line being this one, and this is the interpreter. So we prepare that magic string, this is the name. Here we are saying that we want to identify based on magic byte, because we are checking for this in first line. And then this is offset, which is obviously skipped because it is 0, starting from 0. And this is the magic byte. There is no mask because we do not want to ignore anything from here, so this is also skipped. And then we specify the path of interpreter, and then we write it into the same magical path. And then we check at this location, and we want to see whether it has been registered or not. And if you see, we have it registered here, it is coming from this one. And if we read that, we get to know that what sort of stuff we have registered. Interpreter is this, it is enabled. This is the magic byte sequence starting from offset 0. Then we mark it executable, and then we execute it. And once we do this part, it magically opens in less. So from blue team's point of view, no matter which particular tool you are using, here you will obviously see execv happening. You will correctly identify that this is a process creation, but the file path will point to a text file. And if you are someone who has no idea about this thing, you will try to analyze this file, and suddenly this file is not a valid executable. So you will either figure out that probably this path got overwritten and you missed that file write detection, or there is something wrong with your endpoint monitoring solution, which is putting some sort of garbage data. Okay, in either case, you are going to log a support ticket with the EDR vendor. that, sir, we paid top dollars. What the fuck is this? Are we paying money for this bullshit? Except that EDR is technically correct, the best kind of correct, and it is you who has no information about BinFMT. And that is what I am banking on. So, if by doing this, I am to start less, I can start pretty much any other executable. And in monitoring, you will see this particular path. Mission accomplished for most part. So if we try to intercept the system call, and this is using BPF trace, which uses eBPF to intercept system calls, and eBPF because basically everyone in market is touting, hey, we use eBPF, now give me more money. So here goes eBPF probe, and what I am doing, I am just printing PID, TID, the file name and arguments, all that stuff. So if I execute that, what do I see? This is the process ID, thread ID, this is the path, and that is the command line. What sort of detections or incident response or malware analysis you are going to do here? You can't. And that was the intention. And this is something that doesn't really require any sort of injections inside kernel or any weird C programming or some pointer stuff or cryptic data structure stuff, nothing. Just prepare a string, write it somewhere, and behold the magic. It is as simple as that. Now, if you see the entire process chain, you will eventually see that this less pipe and all that stuff is getting executed. Obviously, you can write a detection at this stage, but the problem is that there are then more ways to hide this part because I already started executing here. Okay, so there are ways to basically deal with this. So effectively, I can make this part disappear, so to speak, and then you will end up with basically nothing useful. So the BPF trace is going to tell us that there is a shell invocation and there is less pipe which is reading the file, but again this is basically modifiable. And then if you see the process listing, you will see this user bin less. Again, this part is modifiable. Okay, a process can rename itself. So if I am starting via BinFMT at the very startup, I can modify my process name and command line both, so it will stop reading like USR bin less. Hmm?
You can enable it to Windows update.
Oh yes, obviously that will not be fishy at all. Okay, and now if you see here, the original PID was these two, 17657, 17658, but if you go to see here, you see that 658 and after that 659 both do not exist anymore. So if you see for this PID, if you want to go back and want to see what parameters did you get, the parameters were this. So at time of event monitoring, you are going to see this. At time of analysis, you are going to see this, and these two are disagreeing with each other. And if I rename this, obviously you will see that yes, some process started, yes, this is some sort of executable file, this is a recognized trusted executable file, which means definitely something is wrong with the EDR agent. Time to raise a support ticket and say some not so nice words to our EDR vendor. Okay. Now this part we already covered. For investigation, the path is pointing to plain text. The original PID is basically gone. And for weaponization, we can do pretty much anything inside interpreter. Okay, and we can make it execute basically anything, a JSON, CSV, image, PDF, office files, audio, video, whatever. or we can basically show some sort of CPU emulator and write rest of the payload for that custom emulator and then use binfmt to start executing that. Possibilities are endless. Okay, and now here the payload, the malicious code, it doesn't need to be in this binfmt handler either. It can be in the file that you are trying to execute. It can be split across two. It can be entirely inside binfmt handler. Again, all these possibilities are open. Now for process rename, there are basically these two ways to rename a process. So you can specify basically any name here, and in the process list the name will be changed. So a process can do this, and this is something that many processes actually do. They will start with very weird looking cryptic command line, and they will then rename themselves to more familiar command lines. So payload can use the same thing. Now obviously you are going to figure out that this is a bug, and you are going to log a support ticket, and then EDR vendor is going to yell at you saying that no, you are stupid and nothing is wrong with our product. Now we come to this RTLD part, and these are the common ways that you can do, and blue team will basically identify that this stuff is happening and it will not really be fun. So what we will do, we will modify the RTLD. Okay, and the thing is that every ELF file can have its own RTLD. So this RTLD part is basically written, basically figured out from that ELF parsing itself. So that means that we can take some ELF, we can use some utility like patch ELF, and we can specify some arbitrary other interpreter. So the same trusted binary will start with non-trusted interpreter, and something fun will happen. And obviously we can basically do a supply chain attack and modify system RTLD itself. And then once we are able to control this RTLD, we can do some stuff like this. So there are some steps that I have given that you can actually replicate and see it happening in your Ubuntu machine right in front of your eyes. So basically what I am doing, I enable the source code repositories because, well, it is open source. I download the source code, then I basically build everything without any modification, just as a sanity check that I am actually able to build it. And then what I will do, I want to preload some binaries from alternate path. So in this source code, I will just change that particular file path to some other path, and then since you are not really monitoring that path because you don't even know that something like this is possible, and obviously you can't really monitor entire system for read activities because that will be utterly stupid, you are going to miss it. So this new code starts looking something like this. Then you make install, then you specify some binary to load, and then you confirm that it is actually working. So in the sleep there are only these two entries. Then I use my RTLD to start the sleep binary. I take the process ID, and then I check in the process map, and I see that SE Linux has been loaded. And again, obviously that is happening from this particular path that is not really being monitored anywhere. So my injection happened, and you didn't really get any other notification that something like this happened. Now we want to make it more fun, and we do not want to do this every single time because this will be stupid. This can be identified in incident response or threat hunting, something like that, and I do not want to be this stupid. So what I will do, I will use patch ELF set interpreter, and I will specify my interpreter for this particular binary, and then I will start that binary, check the process map by taking PID of this particular process, and again this has loaded this SE Linux. So this is even better than previous one because in exec you don't really get the path to interpreter explicitly, you get path for this particular file. Now there is something called trace loaded object, and this is used for that LDD utility that basically tells what dependencies are there. This one. So this actually uses that LD trace object and then these strings are printed by this RTLD, okay, which means that when you do this, you are effectively invoking this RTLD to run, which means that I can do some fun stuff there as well. So for example, wait, I have given some examples somewhere. Okay, so this is what your LDD tool is doing. So what I am doing here, I patch this and then I see that this is coming from system location, otherwise it will look like this. Okay, so if I check that with unpatched RTLD for this one, it will say that libc is being loaded at this particular path because I have modified the interpreter, modified the binary to use some other interpreter, right? And I do not want this path to come in the output because again this will be very much stupid. So I patch it in a way that this line says that this libc is coming from the system location and not the actual location. So that part is again not very difficult. Okay, so again for that we are going to modify some code, and here I am just checking for that this thing, that if it is going to print path for that RTLD, print path for system RTLD instead of our actual one. Similarly, if it is for libc, print path from system libc instead of our actual one, and rest of the stuff is basically as is. And the end result is that our actual path is hidden from the output. In practice, you will do something like this, you will see the output and you will immediately trust it, that yes, nothing is wrong, everything is all right, except a lot of things are wrong, just that they are hidden from the output. Similarly, it can be made to execute basically any arbitrary code. It can do injections, it can leak data, it can weaken cryptography depending upon what sort of stuff you want to do.
When you modify LDD on the system, you require more privilege, let's say, modify LDD.
No, you can do most of these directly from user without even requiring sudo privilege. Assuming you are not going to modify from something from system location. For system location, yes, you will need sudo privileges, or at least privilege escalation to root. But if the executable binaries are writable by user, you don't really need root. Okay, so all these things are basically possible, and then at time of incident response or root cause analysis, you will see that okay, it is pointing to some sort of RTLD, but again, who analyzes RTLD? If you go to some malware analyst, he will immediately load that executable file in IDA Pro or something and start investigating its code, except the malware is not in that ELF, it is inside that RTLD, and no malware analyst is going to reverse engineer this RTLD. So even if you go for malware analysis, this part is very well hidden. Then detections and countermeasures, otherwise blue teamers start crying. So there are bunch of ways for binfmt. This is the file path that you want to monitor for write at least. Okay, and you can check the mount system call for that particular type of file system. You can check for this using insmod system call. You can monitor these two function calls as well in case some process is trying to rename itself. Now for RTLD, you need to verify that interpreter that is associated is actually a valid, known, trusted one. Some software will come with their own interpreters, so you need to monitor that and figure out your monitoring accordingly. And then you need to monitor all other paths where you are hosting ELF or shared objects, and you want to check for any possible modifications there. For countermeasures, this thing you can keep it unmounted if you do not have something installed which actually requires this. And obviously you can also block mount calls which are trying to mount binfmt. You can do that either via seccomp filters. This is the mechanism that is used by Docker and Kubernetes, by the way, to implement their long list of capabilities. So you can use either this, or you can use Linux security module written in either eBPF or in C as a kernel module, and from there you can basically block this. And then obviously you can block file writes on unwanted locations, and for this part you can use either fanotify, which allows you to block writes and reads, or you can use LSM, or you can use eBPF for LSM to implement any of these. So that is all. Thank you. How many of you are willing to drink a glass of phenyl now? Okay, people are still laughing. So next talk will be by